All right, let's get started.
Yeah.
Oh,
We're expecting.
people, take a seat. So our first speaker today is Rahul Kannan. He got his master's degree in 2010 at the Indian Institute of Technology, and then he moved to Heidelberg, where he got his PhD in 2014 at the Max Planck Institute, working with Andrea Macho. He was then a postdoc at MIT, and now he's an Einstein and an ITC fellow here at the CFA. He's worked on a number of problems in modeling galaxy evolution in a cosmological context, including AGN feedback, stellar feedback, the physics of the intracluster medium, and he'll be telling us about the effect of radiation fields in the universe.
Thank you so much. So when I signed up for this talk, I had some other project in mind, but since I have not done anything on that project, I thought I'll talk about something else. And I'll talk about stuff I've been doing in the past year or so since I joined the CFA on modeling radiation fields in the universe. So basically, I'm a galaxy formation simulator. So talk will mostly focus on simulating radiation fields in cosmological simulations. Okay, so why do I care about radiation fields? They are ubiquitous in nature, and they can have, in addition to being an important diagnostic tool, they can also have important dynamical impact in a variety of astrophysical systems. And the scales of this impact can range from less than a parsec, for example, in stellar birth clouds, to almost the scale of the universe. So basically, reionization at high redshifts is basically done by the radiation fields. So if you want to simulate, if you want to understand the effect of radiation fields on all these very different scales, then you need to have a very good radiative transfer algorithm in your code. And that's some of what I'll be talking about today. Okay, so yeah, so as I said, you can have radiation fields from first stars and galaxies reionizing the universe. This is the largest scales. Then you can have radiation pressure from high luminosity quasars driving large galactic scale winds. These are the order of hundreds of kiloparsec scales. And then you can have a small scale, less than a parsec scale effect, where radiation fields from young ONB stars photoheating the gas in the surroundings and changing the ambient pressure and temperature of the gas around young stars. Okay, so at a subparsec scale or parsec scale, as I said, you can have star. This is the composite image of 30 Doradus, where you have extremely young stars, and this is all hot gas. And this pre-processing of this stellar birth cloud is mainly done by radiation fields and stellar winds. Supernovae have not gone off in this region yet. So it's basically, you're already having some form of feedback even before the first supernovae go off. So if you want to simulate this effect, then you need to have an efficient RHD code. Then if you want to have, this is a image of a quasar, so that you cannot see much. It's basically a point source. But you can have these highly luminous sources which can drive outflows by just radiation pressure on the surrounding medium. And then on the larger scales, you have reionization. So the first stars and galaxies form at about redshift 15 or 20 or so. And then they inputs huge amounts of ionizing radiation, which forms these H2 bubbles around these sources. And as they expand, they merge and they completely reionize the universe by redshift 6 or so. And especially with the upcoming instruments like HERA, SCA, JWST, and WFIRST, which are specifically designed to look in this region, it is important to understand this process and get accurate theoretical models so as to understand this process more accurately. And all of this, as I said, requires efficient radiation hydrodynamics simulations. So let's start with what is radiative transfer. So this is the basic radiative transfer equation, where I nu is the specific luminosity. And so this basically tells you how the specific luminosity changes as a function of time and space. This is basically kind of a conservation equation if you exclude the source and the sink terms. So as you can immediately see, it's computationally intensive because you need to discretize this equation not only in time and space as you do for the pure Hydra equations, but you should also discretize it in the frequency and the angle variables. And so this makes it a very computationally intensive. So the popular method of solving this equation is using something called ray tracing, where you solve this equation along each ray and you cast the rays in every direction possible from the source. The problem with this scheme is that you need to cast rays in every angle possible from every source possible in your simulation. So it becomes computationally intensive quite fast. Instead, what you can do is you can take the moments of this equation with respect to the solid angle. So that's in the left here in your perspective. So the 0th moment is the J nu first. So that's the stellar photon energy density, the photon flux, that's the first moment, and the photon pressure tensor is the second moment of the I nu. And then you can write down, so you take the 0th and the first moment of this equation as well, and then instead of writing down this equation, you can write down two equations here, which are basically conservation laws for the photon number density and the photon flux. Okay, and so you have two equations here and three terms. So you have the photon number density, photon flux, and the photon pressure tensor. So you need an additional equation to close these set of equations, and that's the closure relation given here, which is the Eddington closure relation, which is commonly used, where your photon pressure tensor is related to your photon number density by the Eddington tensor. Now this form of Eddington tensor is much debated. A lot of people use a lot of different forms of this Eddington tensor, or the closure relation as they call it. We choose to use the M1 closure relation, which is basically the simplest approximation for this closure that you can make. Well, it's a step higher than the simplest approximation for this closure relation that you can make. And it is an approximation which gives you the radiation fields as a function of the local properties of the cell, which basically means that the tensor is independent of the number of sources in your box. So this makes this scheme extremely fast, and you can do large-scale simulations with this method, which has recently been shown here. Okay, so we solve, as I said, these two conservation laws, and using similar to what is done for hydrodynamics in normal code. So you basically have two conservation laws, and then you use a Riemann solver to calculate the flux on the left and right states of the interface of the cell. So these are all technical details, but I can show you one or two more technical plots, and then I can go to the scientific results. So as I said, people have done this before. So for example here, Ramses RT has a similar kind of scheme. But what we did is something go beyond that. So this is, for example, in a test, idealized test, we calculate the error as a function of resolution elements. This is our epo-RT, which is what I implemented, and this is what previously people have implemented. So as you go with resolution, you can see that our error decreases considerably, and that error is proportional. The decrease is proportional to n squared, whereas for previous schemes it's proportional to n power minus 1. You can say, why does this matter? So I show you a test which shows why this matters. So you have, for here example, you have incoming plane parallel wave of radiation, and from this end of the box, and the other three boundaries are sinks. So this is a source, this is a sink, and this is just IR radiation heating up, coupling with the dust and heating up the dust gas fluid. So if you have kind of an Ramses RT scheme, so with 32 square resolution elements, the maximum temperature you can heat the gas up to is about 200 Kelvin. And if you use their scheme and replicate what they did in our code, then you kind of match their results. So the black lines are the Ramses RT results, and the green lines are the Arepo RT results. Whereas if you go to 1024 square resolution elements for Ramses RT, then you get these black lines, and those you can heat the gas up to 400 Kelvin instead of 200 Kelvin, okay? A bit more than 400 Kelvin. Whereas with the 32 squared resolution elements and with our fiducial scheme, which reduces the error much more, has a better error control, you can reproduce their 1024 square with just a 32 squared resolution elements. So this is why this is important. So even with a very low resolution, you can reproduce the accurate result. And that's why this is extremely important. Okay. So just to summarize, Arepo RT, it's just a radiation hydrodynamic extension to the moving mesh Arepo code. It's accurate and efficient. You have full second order convergence. And it has a lot of very good properties, including the fact that we can do UV photoionization and IR dust scattering, multi-scattering with this scheme, and it is applicable in a wide range of environment. So I'll just show you some examples of some of the environments we have applied this scheme to. So the first is early stellar feedback, or the effect of radiation fields from young stars on its surroundings. So just to give you an small introduction to this. So this is a plot which as a function of time, it shows the specific luminosity of a star particle in an IMF average sense. So the bolometric luminosity from the stars is an order of about 2 to 3 orders of magnitudes higher than the energy injected by the supernovae, right? So you have a lot more energy in the form of radiation than from just supernovae. But many of the current models just use supernovae feedback. If you want to know what these radiation fields do in addition to this, in addition to supernovae, we need to do radiation hydrodynamic simulations. Okay, so people have tried to understand what these radiation fields do, and they have come up with some kind of unrealistic subgrid models. And I have also done this previously. So for here, I show there is some subgrid model for photoheating, which assumes that about 10% of the bolometric luminosity thermalizes around a star. And if you do that, then you can reproduce the stellar luminosity function at high redshifts, for example. And that's shown here. So if you do not have any photoheating, then that's the red line. If you do, then that's the green and the blue line. So if you include this effect, then you can get the right luminosity function or the stellar mass function, whatever you want to call it. But the problem is, you know that 10% of the bolometric luminosity cannot thermalize around a star. We don't know what fraction thermalizes around a star. So this is kind of an unrealistic subgrid model. Other people have invoked radiation pressure from radiation fields. So here, for example, it's a Milky Way galaxy, and they assume that the optical depth or opacity to dust is 30 or 50 or even 100, right? So this cannot be true. If you do Milky Way kind of simulations, you get a factor of 5 to 10 boost in the opacity. So 30 or 50 is unrealistic. And even if you see the morphology of the galaxies with these high opacities to dust, you see that the disk, the feedback just blows up the disk, and you do not get realistic thin disks in your simulation. So although people have tried to understand what radiation fields do, they have been quite unsuccessful, and they need unrealistic parameters in order to reproduce the right results. So instead, what we do is we actually do fully self-consistent radiation hydrodynamic simulations, and we choose the mass and the spatial resolution to be about 10 solar masses and 0.1 parsecs. This allows me to resolve the supernova, set-off Taylor phase in the supernova, and also to resolve the Stromgren radius of these simulations. And I perform 4 different simulations here, one with just supernova, one with supernova plus photoheating, one with that plus radiation pressure, and the last one with IR radiation pressure as well. This is done in order to see which mechanism is the most important. So this is a result. So for example, we have the red line is with just supernovae, and the others are with radiation fields. And you can immediately see that the radiation fields reduce the star formation rate and the stellar mass by about a factor of 2. And it's also clear that radiation pressure does not play an important role, at least in these low surface density galaxies. And so what this does is it increases your gas depletion time scales, and it brings it closer to the canonical 1 giga-year value. That's the left plot here. And then the right plot, I show that because of photoheating, the mean density in which the supernova goes off is reduced. And this is basically why you increase the efficiency of the supernova feedback, because you increase the momentum output of the supernova, and that's why you reduce that's why you reduce the star formation by quite a bit. Okay, so basically, just to conclude this part, so including radiation field reduces the star formation by a factor of 2. It reduces the gas. It increases the gas depletion time scale, and so and it tells you that photoheating is the most important mechanism which regulates star formations in these low density galaxies. So the next part I'll talk about is reionization simulations. So here I'll just show you. This is a 6 megaparsec box. With the sources of reionizations are just stars here. And this is just the volume weighted H1 fraction as a function of redshift, which is given here. And then I can run this movie. And you can see how reionization basically proceeds inside out. So you reionize sources, regions close to the sources, and then eventually it goes outwards and reionizes the whole universe as such in our simulation model. So by tuning the escape fractions, we can basically match the reionization history of the universe, which is given here, and also the Thornton scattering electron depth, which is given, and the black line is basically the estimate from Planck, 2018. So we match both of those results very well. So the first thing, science result we are looking at is if you generate the radiation field self-consistently and a UV background self-consistently from your models, can you get a drop-off? Can you affect the low mass halos? So can you basically reduce the star formation rate and the stellar mass of low mass halos? And so you can see that previously people have shown that if you include radiation field self-consistently, you can see a significant drop-off in the star formation rate of galaxies and in the baryon fraction. When we do look at the same, we do not see such a significant drop-off. So the blue line is with the UV background from Hart and Maddow, and the red line is from the self-consistent UV background. Only if you reduce the feedback model that we have, only if you reduce the effect of feedback model that we have, can you see this big effect. And it is the same for the baryon fraction as well. So we can kind of conclude that the previous models were incorrect in saying that you can reduce the star formation rate and the stellar mass of small halos significantly. The only reason they could get that result is because their feedback in the first place was inefficient. So if you have a good enough realistic feedback mechanism, then the radiation does not really reduce the star formation rate in these low mass halos. Okay, and finally, I think which is 5 minutes or so, I will talk about something which is a high energy phenomena as such. So I'll talk about outflows from high luminosity quasars. So just to give you an introduction, in simulation, in cosmological simulations, people invoke two kinds of modes of feedback. So it's the radio mode and the quasar mode. And radio mode is the mode which keeps the clusters or massive galaxies quiescent. So here you can see the gas fractions as a function of radius in the illustrious TNG simulation. So that's the gray dashed line is the observational result, and the pink line is the result from the illustrious TNG. And you can see that in order to make the clusters quiescent and non-star forming, they blow out almost all the gas from the center, so you have much less gas in the gas fractions in the center, but they pile up all the gas in the outskirts. And that's how they do it. So the only way they can make this quiescent is to blow out the gas from the center and pile it up in the outskirts. And this is not true just for the TNG. This is true for Eagle, Sea Eagles, Romulus, any of the most recent simulations. Any of those simulations you take, this is true. You never match the gas fraction profiles. So you can say, okay, so the radiation, the AGN feedback is too violent, and that's why you're reducing this reducing the gas fractions here and piling it up here. You can try to make it less violent, and this is work we have done by including thermal conduction. It just makes the radio mode less violent, and you get better match the cool core fractions, for example. But you still pile up a lot more gas in the outskirts, which is basically telling you that it's not the fault of the radio mode that this is happening. You're not blowing off enough gas at high redshifts, so the quasar mode is not doing enough work. So if you can blow up most of the gas at the high redshifts itself, then you do not have to do too much work in the low redshifts. So that's the idea we are going with. And the idea is that if you have radiation pressure driven outflows in high luminosity quasars, then you can blow out most of the gas from the halo, and you don't need to do it at low redshifts. So we have tried this. So we initialize an NFW halo, and we inject radiation isotropically into this halo, and we assume a constant dust to gas fraction, and we allow the radiation pressure on dust to drive large scale winds. And so here is a plot which shows the density, velocity, UV radiation field, and the IR radiation field, reprocessed IR radiation field. And you can see, you see that you can drive outflows of the order more than 1,000 kilometers per second just by having radiation pressure on dust. And you can match the analytic expectations very well. So the solid lines are the analytic expectations, and the shaded region is our simulation. Okay. But that is just a normal a dust to gas ratio which is constant throughout the halo. You know that is not true. You have a galactic disk where you have much more cold gas and much more dust in the halo. So we try to replicate that by allowing a disk to form in the center of this NFW halo. And what this does is that it increases the optical depth to the dust. So here, as a function of radius, I plot the optical depth. This is if you have a constant NFW, the purple line. Anyway, blue line is the constant NFW halo, dust to gas ratio of 1%. If you allow a disk to form, then you have this line here. And if you have dust formation physics, then you have more dust forming in the center, and that's this line here. So just by allowing galaxy formation to happen in a halo, you can increase the optical depth by a factor of 100, right? And so this can drive much larger outflows. So on the left here, you see if you include a AGN with a luminosity of 10 power 47 ergs per second, then you can just drive an outflow in this direction. It's not collimated. It's collimated due to the disk, basically. You basically destroy the disk by having this luminosity AGN going off in the center. But there is a caveat here. We do not assume any dust destruction in this regime. But if you assume that there is some kind of a dust sputtering, because if you have high enough velocities, you can shock heat the gas to 10 power 7 Kelvin, then that sputters the dust mostly in the shocks, and then you reduce the velocity of the outflow. You do not destroy the disk, but you still drive a small scale or a large scale outflow into the halo. And that is shown more qualitatively here. So if you have no destruction of dust, then the momentum output and the energy output of the outflow is extremely large. Those are these two top lines here. If you have dust destruction, then they reduce by quite a bit. But you can still drive large-scale outflows with this mechanism. Of course, there's a lot more to be done. This is just these are some of the first results that we have done. So we need a self-regulated model for radiation, for black hole feeding and feedback from radiation pressure. We need a better model for ISM, and all these things we plan to do. So I'll just conclude with an outlook. So I've implemented an accurate and efficient RHD solver. I've already used this to address important questions on a wide range of astrophysical system, all the way from subparsec to gigaparsec scales. And so there are a lot of projects which I plan to do in the future. And if you have any more projects in mind or would like to collaborate on any of these, please let me know. Thank you.
Questions for Rahul?
In the last piece,
Yes.
two questions. Do you allow for line driving by the UV?
We do not. This is just on the dust, radiation pressure on dust.
The dust, do you allow for destruction by X-rays?
Yes. So those will be subgrid. That'll be below our grid scale. So here we do not do that, but at some point we should include that at some point. But yes, most of the dust in our models is just destroyed by sputtering. Once you have a shock-heated gas which reaches up to 10 power 7 Kelvin or so.
We have these really broad energy bands for the radiation field. The heating depends on what you assume for the average photon energy.
Sure.
What do you assume?
So you can make it as broad or as. So let's see, where is that? So here, we try to make the radiation bins as small as possible in the regime where you actually have the ionization front, where the ionization energy is. So for H1, for example, it goes from 13.6 to 15.2, for example. And so for all these things, we make it as small as possible. And for the higher energy bins, where we do not have chemistry, we make it as broad as possible. So that is an approximation, of course, but we kind of recover the right results.
Any other questions? Let's thank Rahul again. And our next speaker, I'm going to apologize for my terrible accent. Our next speaker is Rozenn, Boissay, Malaquin. She got her master's in Strasbourg, France, and then she moved to Switzerland to get her PhD in Geneva, where she was working with Stefan Fontani. And there she was working on various aspects of the AGN emission, especially focusing on the soft excess. She has been a postdoc at MIT since 2016. There she's working with Herman Marshall and with Mike Nowak, doing a lot of Chandra grading, data analysis, as well as other things. Today she's going to be telling us about relativistic components of the ultra-fast outflow in the quasar PDS 456 from Chandra, New Star, and XMM.
Thank you very much. Thank you very much for inviting me. Oops, I forgot to put this. Does it work? Yes. Perfect. So my name is Rozenn Malaquin. Thank you for pronouncing it correctly. So I'm a postdoc at MIT for 2 years now. I'm working with Herman and Mike and also with Claude. And I will present a work I have been doing also with Hash about the relativistic components of the ultra-fast outflow of this quasar PDS 456, that is a very luminous quasar, using Chandra HETGS, New Star, and XMM Newton data. So first of all, warm absorbers are detected in many AGNs, so through absorption lines in X-rays and in UV as well. They have velocity that have 100 or 1,000 of kilometers per second, but they can have also higher velocity, up to 0.4 C, for example. In this case, we call them ultra-fast outflows, or UFOs. And they are observed through blue-shifted, highly ionized iron absorption lines, above 7 keV, in many AGNs. They can reach some outflowing rates of about 1,000 of solar mass per year, for kinetic power that is very large as well. and they are thought to be launched from the accretion disk at a few gravitational radii from the supermassive black hole. There is a link that exists between the galaxy parameters and the supermassive black hole growth. For example, this link between the mass of the black hole and the velocity dispersion. And it is thought to be regulated by AGN feedback processes, and in particular via these powerful winds. And this is illustrated here in this scheme. So as the mechanical power of this UFO can reach a few % of the bolometric luminosity, in this case it can affect the host galaxy. And doing this, in fact, it's sweeping away the galaxy reservoir of gas, and hence it's quenching the star formation. So that's why it's very important to study these UFOs for AGN feedback in particular. PDS456 is a well-known object, a very bright quasar, as you can see here. You can't. Does it work? Here. It's also accreting almost at the Eddington limit. And as you can see here, you have, so it has been observed several times by many satellites. And you can see that in all the cases, so here RXTE, Suzeku, and XMM, you have this absorption feature, strong absorption feature here, 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 and here. So above 7 keV, that has been explained by as a signature of a UFO with a velocity of 0.26 or 0.3 c. And so it is explained, it has been identified as the absorption line from the iron 26 Lyman alpha. So in this paper in particular, so from Nardini, in a Nature paper, they used XMM and NuStar data that were simultaneous. And you can see still here this iron 26 Lyman alpha absorption line that is blue shifted. And you have also this line in emission that is blue shifted as well, but not as much as this absorption line. And the most interesting part of this paper is that you have also, it has been identified, this line here, the Lyman beta, and the hedge as well from the iron 26. So instead of having just one signature for this UFO, you have 3 of them. So that's perfect. They are blue shifted at the same blue shift, so that's why it comes from the same UFO. Here you have a plot that shows that this object is very variable in X-rays, but in all the cases you can see also that you have this absorption feature at high energy. And also in UV, you have a signature here that could come from an outflow of 0.3 c, a velocity of 0.3 c. And very recently, this year, Reeves, in his paper, claimed that they found a second UFO, even faster UFO, as you can see here. So they said that they identified this absorption feature here as also an iron 26 Lyman alpha absorption line, but blue shifted, but by even higher velocity. So what we did for this paper is to look at different data sets. So the first one here with Chandra HETGS and NuStar data, 2015. So this is the blue data here. We also analyzed some old Chandra HETGS data, 2003, here in green. And we reanalyzed the data used by Nardini, so XMM and NuStar data from 2013-2014, combining them together. So we have this red data here. So we performed the analysis with ISIS. And first of all, we determined the continuum. So we modeled it with a power law, also a partial covering absorber in order to reproduce the curvature that has been found around 5 keV. We also took into account the fact that we need a cross-calibration factor because we have data from different satellites. And we also modeled the soft excess that is present in this object. So we used for that a broad Gaussian. So it's not very usual to do so. Usually we use a black body or a Bremsstrahlung. But we wanted to, as we are analyzing the same data as Nardini, we wanted to be consistent with this model. So we use this one. So first of all, we looked at absorption features above 9 keV. And to do so, we fitted the data with sets of Gaussian lines. So what we did is to take one Gaussian line in emission, two Gaussian lines in absorption, and a hedge. We linked together the blue shift of the absorption features and the width as well. And we fitted that to our data. So Chandra and Nustar, and here XMM and Nustar. And you can see here that we found these lines that are significantly detected and with a velocity of 0.27 c. So it's perfectly coherent with the result from Nardini and from other papers as well. What we wanted to check also is if there is this second UFO that has been claimed in very recent data. So to reproduce this second UFO, or to try to look for it, we applied a second set of Gaussian lines, so the same, two absorption lines and a hedge. And what we found is that we have the Lyman alpha of the first UFO and the Lyman alpha and the Lyman beta of the second UFO that are detected significantly in both observations with this velocity, so 0.26 c, coherent with the previous results, and 0.47 c, so it's consistent also with the results from Reeves, who claimed that they found a faster UFO in data, more recent data. So applying this second set of Gaussian lines improved the fits. It improves also the residuals. For example, if you look at this part here. Voilà. We also applied a P Cygni profile, so we did the same as Nardini in his paper, using the same model. So to model the expansion of spherically symmetric stellar winds, so it's a model from Chris Dunn that we used. So we applied one model and also a second one in order to try to model the second UFO, the possible second UFO. And what we found is that the fit is improved by applying this second model. And this is the velocity, the infinite velocity that we found. So it's a bit different from these two ones, because in fact it's not measuring exactly the same thing. It's the actual speed of the wind, this one. And the other one is the line of sight velocity here. But we will keep the other velocity for the following, because this one is very model dependent. It really depends on the model you use for fitting this P Cygni profile. So we have looked at all the lines at high energy individually. What we wanted to check also is to look at other lines at softer energies. So we did a blind line search. So we took the continuum, we fixed all the parameters. We added a line in emission or in absorption, it was able to choose. We fitted this line, we freed the continuum, we fitted all the parameters, we fixed all the parameters 50 times, and then we kept only the significant lines. And this is what we have, for example, for the data, the Chandra and Nustar data. So we identified some of the lines. So here, for example, in orange, you have the emission lines that have been identified. In pink here, you have the absorption lines from the partial covering absorber. Here in red, you have the absorption lines from the slowest UFO, so the one found by Nardini and so. And here you have, in green, the absorption lines from the fastest UFO. So as you can see here, so you found again the results from when you looked at the data, when you looked at the lines line by line at high energy. So you have a signature of the iron 26 Lyman alpha here, iron 26 Lyman beta here. You have also some contribution from iron 25 here, and also from nickel here. And you have also for this line that is quite broad, right? Possibly contribution from iron 26 Lyman alpha, but at higher velocity. And here you have the Lyman beta that is detected also here with a contribution, possible contribution from nickel. And what is interesting as well is to look at softer data. So here, for example, you have a line that has been identified as coming from the softer, from the slowest UFO, and here from the fastest UFO. So it's the first time that we see such signature at lower energies. So we looked at the data, at the lines, line by line, but what we wanted to do is also to model with a photoionization model. So to do so, we used war maps, so the analytic model war maps, instead of using X-star grids. To do so, we applied this SED that has been used for all the previous works as well. We just slightly changed the slope of the X-ray part here in order to match our Chandra data. We kept the UV the same. And so we apply a photoemission model. We changed this partial covering absorber using also war maps. We applied a slowest UFO for all the data and a faster UFO for the Chandra and NuStar and XMM and NuStar data, not for the Chandra data alone because we don't have data at high energy, so it will be useless to do so. And a warm absorber also for the data with XMM. And we did an MCMC in ISIS. And this is what we get as a result. So for Chandra and NuStar data. So here I plotted all the lines that are the strongest lines predicted by the model. So here again, you have the emission lines in orange, the pink lines that are from the partial covering absorber, red lines from the slowest UFO, and green lines from the fastest UFO. And you can see that it's consistent with the identification we have done looking at individual lines with our blind line search. Still with these strong features at high energy. So we did so for the three observation sets. So the wind emission is slightly blue shifted, as you can see here. It has turbulent velocity that is quite large, but it's consistent with previous results, previous works. The partial covering is lowly ionized, as you can see here, compared to the slowest UFO, where you have a high ionization. It's a log C here. And so this is the velocity of the slowest UFO, so 0.29, 0.24 C. And here, for the faster UFO, you have 0.48 C. So it's consistent with the results when looking only at the lines, line by line, I mean. And you have also you see also that you have an improvement that is more significant for the XN data by applying a second UFO. Here you have the results of the MCMC. So you have the ionization as a function of the column density. And here the velocity in absorption as a function of the velocity in emission. So for Chandra and NuStar, XMM and NuStar, and Chandra alone. Here you can see that, well, the parameters are better constrained. That's normal because we added several observations together, so we have a better signal to noise. Here for Chandra, it's less constrained because we don't have the data at high energy, so that's normal. But what we can say is that in any case, you see that the ionization parameter and also the column density are quite consistent between observations. And this is also the case when looking at the velocity of the outflow. So we wanted to check at the thermal stability curve. So we plotted this S-curve here. So here in blue, you have the curve for XMM and NuStar data. Here in gray, you have the curve for Chandra and NuStar data. We overplotted, so when you are in this curve, you are in thermal equilibrium. We overplotted the results from the photoionization modeling. So here you have the WAM absorber for the XMM and NuStar data, the partial covering absorber for all the data, and also the UFOs that have been detected. You can see that these two groups here and here seem to be stable because they are in a positive branch of this thermal curve. But something strange is that these UFOs are in an unstable branch. They seem to be unstable. But the thing is that we have seen that these features are seen in all the previous data, in all the observations. So they have to be stable in some way. So maybe, and also something else, this S-curve has quite an unusual shape. It's not really a perfect S. So maybe there is something that is not completely true here. Maybe it's not the correct shape of this curve that maybe should be like this. In this case, the UFO would be stable. Maybe it is due to the fact that this S-curve is really model dependent. It really depends on the model you choose for the SED. So maybe the SED we choose was not precise enough. We also didn't took into account infrared data, so maybe it could play a role in the cooling. There is something that is strange here. Or maybe it's just that our UFOs are not in thermal equilibrium, but maybe in radiative equilibrium. Work that has been done on these UFOs by Matze is to look at the velocity, the correlation between the velocity and the intrinsic luminosity. Using many observations, they found a strong correlation that is supporting the fact that the wind should be radiatively driven. This is also supported by the fact that you have an Eddington ratio that is almost 1. And so we checked for this correlation using our 3 observations and also the one from Reeves. And we found a possible correlation, so not something very significant, but still going in the good direction for supporting this radiatively driven wind. And here we calculated the UFOs parameters. So the inner radius, here using this formula from Reeves for radiatively accelerated winds. So you can see that you have the slowest UFO that is a bit further than the fastest UFO. And this is represented here. And we calculated also the mass accretion rate for these UFOs, 3 to 20% of the mass accretion rate, and 7 to 40% for the second UFO. And we calculated also the kinetic power here for these both UFOs. And we found that we have 0.8 to 8% of the bolometric luminosity. So as I said in the introduction, it's sufficient in theory, to induce significant AGN feedback. So that's why it's very important in this object. And here I plotted, well, I took a scheme from Mathieu, who plotted this, this representation of this wind, because in fact, it is thought to be the same wind, a clumpy wind, made of several components. So UFOs that are represented in red here, closer to the black hole, and then more ionized as well. And here, further, a bit further, you have the partial covering absorber that is less ionized as well. So this is a nice representation of this UFO in this object. So to conclude, we studied simultaneous observation with Chandra, HETGS, and NuSTAR data from 2015. We analyzed all Chandra HETGS data, and we reanalyzed XMM Newton and NuSTAR data. And we confirmed the presence of this first UFO that has been found in previous work. So with a velocity of 0.29 C. So that's great. And we confirmed also the presence of a faster UFO. So as the one found in very recent data, with this velocity, 0.48 C. But we saw also this presence of this faster UFO in XMM and NuSTAR data. In this paper, they claim that they don't see it. So we did something different, I guess. It's not very well described how they have checked for this presence in, I mean, in the data from Nardini, 2000, this one. So maybe it's also because of the fact that we combined all the data together, so we increased the signal to noise enough to be able to detect this UFO. So also we checked, we found this using several methods that led, fortunately, to the same results. So we used several sets of Gaussian lines in order to model the iron K lines around 9 and 11 keV. We applied also some P Cygni profiles. We looked for lines at lower energy. So we identified some blue shifted lines in HETGS spectra, so from silicium, sulfur, oxygen, neon. And we looked also at iron and nickel lines at higher energy. And we applied also photoionization modeling using this WAR-MAPS model. So all this resulted in the same conclusion. So we detected these UFOs that are highly ionized and dense as well. The partial covering absorber is less ionized, less dense as well, and its covering factor is changing between the observations. And the most interesting part, I guess, is that both relativistic components of these outflows are powerful enough to play a role in the evolution of the host galaxy, because you have a mass outflow rate of 2 to 20% and a kinetic power of a few percent or so of the Eddington values. Voilà.
I have a naive question. Maybe I'm misunderstanding something, but the fact that you're quoting this mass outflow of 2 to 20%, and on the previous slide, it was even more than that, I guess. Yes. So if you take the upper limits, it can go to 60% of Eddington.
Yeah.
So does it mean that you have the Eddington limited accretion, but basically half of the mass that isn't falling is not actually contributing to the growth of the black hole, and it's moved back, like out?
Alors,
so the effective black hole growth rate is less than the Eddington.
Alors the thing is that also this formula here is based on the inner radius that has been calculated here.
Okay.
So maybe it's playing a role. I mean, this as you can see here for the second UFO, it's a very small inner radius, so it's something very constraining. Maybe it's not so constrained, I mean so close in reality. It's really based on this assumption. So probably plays a big role on that value. It took me a while, yes, to to compute it. Yeah, especially the MCMC. But
parameters were you allowed to fit freely there? Because it's got dozens.
alors, well, how many do I have? So this is fixed. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So yeah.
That must literally have taken months.
It's yes, yes. It was a bit hard, and we choose also to fix to link some parameters in order to to make it to improve the time computing. For example, this this is important also. I didn't say we linked the ionization parameter for both UFOs in order to help the fit. But it would be better, of course, to make them separated because as you have seen here, it's not located at the same place, so it should not have the same ionization. But the signal-to-noise of our data were not enough to allow us to do so. We also fixed this parameter here, the turbulent velocity, and we linked also the partial covering absorber and the slowest UFO in blue shift, in velocity, again to help the computing and the fit.
What did you use for Warmap's materiality, like abundance?
The what, sorry?
Warmap's abundance?
Solar, yes.
You said that was a very strange shape.
Yes.
So-called S-curve. And yet your SED looked pretty ordinary.
Yes. Ouais.
It's entirely determined by the SED. So
Yes.
So why? Do you have any clue what's wrong?
Alors,
Or why you disagree? Everybody else might be wrong.
maybe. The thing is that, well, it's usually not this shape, right? But because also, usually you cut it here. You see this part, but not this part, right? So maybe it's just because we look at a larger range of ionization parameters that we see that there is this shape that is not commonly seen in other works.
At the high value, high temperature, you usually go to a constant temperature.
Mm-hmm.
Which you work out for this SED.
Yeah, yes.
Where it's going to? Is it unusually low constant temperature?
I don't really know what is happening in here. It's quite strange. I totally agree that it's... But I mean, in any case, this UFO should be stable, right? So, because they are persistent. So, that's quite strange. I agree. If someone has a clue of what is going on here, please tell me.
Last question.
Sure.
Question. Do you expect those UFOs to be a common phenomenon in Eddington limited quasars and AGN, or is it something really exceptional about this?
No, I think it's quite common because of this in particular. If there are radiatively driven winds, if you have an Eddington ratio that is high, it's consistent. So it will be. In fact, we have seen. We have seen these UFOs in many objects. Apparently, it's 40% of AGNs, so that's quite huge. But it's also this kind of UFOs with such an extreme velocity. I guess it's better. I mean, it has a better chance to happen if you have a higher Eddington ratio. Yes.
I just wanted to mention that Rozenn is happy to stick around CFA this afternoon, so if anyone would like to meet with her, please just come up right now. Let's thank both speakers again.
Hello, thank you.
You want to come by my office after?
Yeah,
you're
sure.
done?
Ouais.
It's
That's pleasure.
B219.
Oula, ouais. It's the first time I'm coming here, so I don't know where it
Turn
is.
off the mic.
Huh? Oh,
Turn
yes.
off the microphone.
Thank you.
Should be a little switch. Yeah, it's right there.
No, it's not that.
Switch.